Our
This
focus
conference will now be recorded.
has now been on safety.
Frank, I'm sorry to interrupt you, but are you sure you're sharing? Because I don't see anything.
Oh my. Let's see. It says that I'm sharing. In fact, I see my screen in the go to meeting window. Can someone else confirm?
Yeah, we can.
I can see it. Yeah.
All right. So I'm not sure what the issue might be for you, but I think everyone else can see my screen. Okay. Yeah. So I'd like to make everyone aware that LaTeX has evolved a lot over the last few years. In particular, we've expanded our offering to cover not just architecture analysis, but other key areas of software and system development. During this webinar today, we want to talk about these 5 ways that how you can improve your control of your system, integrate it with DevOps, minimize testing, find gaps in requirements, and how to produce artifacts that will be useful in achieving compliance. These solutions you heard about Code Clinic. Code Clinic is the LaTeX partner who has consultants such as Neil Langmead, who can help a company adopt these various solutions depending on what's important and what the issues are in your software development activities. So with that, I'd like to turn it back over to Neil. So if possible, Michael, you could make Neil the presenter.
Should be done.
Hi everyone, can you hear me?
Yeah, we can hear you, Neil.
Awesome. Can you see my screen?
Yes, I can.
Okay,
No,
great.
not yet. Here we go.
Okay, yeah, so I'm going to show a simple example. It's a C and C++ library. It's an open source software that's used in embedded systems, and it's called ISO AGlib. And it's a nice example. It comes with its own architecture diagram that you can see here. And it's a layered architecture that somebody has used to express the intention of the designers of the system. It's a layered system that has components that interact with each other. These arrows indicate a system providing a service to another layer above it. And these colored modules here, they indicate optionality. So they are optional modules. They may be included, they may not be included. So it's kind of a plug and play architecture. And these colored modules here that you see are required parts of the system. As often happens though, people do a diagram like this at the beginning of a project, then the project gets developed and the actual real architecture gets a little bit murky. Maybe it goes to spaghetti code in certain cases. Developers create bad dependencies between layers where there should not be any dependencies. Maybe there's a coupling that is introduced between modules, which would mean that we cannot have that independence. These kind of things happen over time. We call this architectural erosion, where the architecture goes from bad to worse. And what we can do with LaTeX is several things. Firstly, visualize the as-is architecture. So where are we today with our architecture? How does it look? We can use this to document the existing architecture as well. We can use it to update this picture to reflect the real implementation. We can also use it to make changes to the architecture, which is called refactoring. So we want to change the dependencies, decouple components from each other, get back to the original plan in some cases. And we find when we do that, we have consequences for both the build and the test. If you have a highly decoupled architecture, it really speeds up testing. It really speeds up the build as well, because you can build components independently. And so what I'm going to show you is is lattice an architecture-centered approach to building and releasing software, hence the focus on the DevOps pipeline, because truly if you can decouple, you can accelerate the building through parallelization on a DevOps infrastructure such as Kubernetes or Terraform orchestration. And using those techniques of independence, we can then actually speed up the build over a distributed system. But first, let's have a look at this particular piece of source code, which, as I say, comes with an open source library, and we're going to visualize that in lattice. And the first thing you see is something called a DSM, a dependency structure matrix. And the way we read a DSM is that the columns are using and the rows are used by. So for example, com is using the component called scheduler 723 times. And you can see those usages here. Every possible type of C and C++ relationship is actually visualized. And you can see in this situation, com is using scheduler, or if I read across the row instead, scheduler is providing services to com and is used by com. So the dependencies that we visualize are everything from the abstract syntax tree of C and C++. We use the CLang front end. We can also use a number of static analysis tools as the front end, such as Clockwork, Axivion, and a number of others. We also can import data from testing tools such as Cantata, which I think many of you use, which uses the EDG front end, and visualize dependencies that way between our objects. So typically every dependency in C++ that we're interested in are things like function calls, global data, read and writes, and all of those are displayed between functions, files, classes, enumeration types, and structures typically. The first thing we usually do when we import and visualize an architecture for the first time is called partitioning. And partitioning is a set of algorithms that will sort the application according to the algorithm that we choose. And typically for software, we want to do a component partitioning, which sorts by usage. It puts the things that are used at the bottom, and it puts the calling code at the top, and it will reveal to us the structure of our code from a top-down perspective. And as you can see, the partitioning put the COM components at the top. So that's reflected in the original architecture of this picture. And hardware and drivers is towards the bottom, which is here. And we have some components which are actually not described in the architecture as well. And generally, we have a lower triangular system, which is what we want, because that means things above are only using things below. If you have relationships above the diagonal, that means you have a lower level component like util is using com here, which is quite high up in the architecture. That's usually undesired because you have a utility which should be a provider is using something up in a higher layer. And so this would be a candidate for refactoring and restructuring. Similarly, driver here down below is using something in at the top of com here, which is also bad because you have a low level system using something here, and the greater the distance from this diagonal, the greater the coupling, and the greater the impact of a change. In fact, that's something that people use lattice a lot for, is to simulate the impact of a change, because if I changed any element of my system, which could be a function, it could be a file. Here we have a utils.h, which is heavily used. If I mark this as changed, I can run an impact analysis on this changed file to transitive closure, and it will compute for me the rippling effect of changing that file on the whole architecture. And as you can see, changing that particular file leads to 9 levels of impact. Everything here is used by everything here, and then everything here is used in the second level of indirection until we get to the outer layer of impact. and we have the complete effect of changing that particular file on the system. And we got excited because it was this data actually that we realized would change people's pipeline experiences. As you know, in functional safety projects, the number of lines of code is going up and up, complexity is going up. You cannot feasibly run every test with every change. And so the certification challenge is, what happens if I change one line of code? How do I recertify my library or my application? And that often starts with an impact analysis. How does changing this file impact my tests? How does it impact my requirements? How does it impact my build and my test phases? And that's the question we have solved with a number of medical devices and automotive companies now, as they look to do something called change-based testing. I only want to retest the parts of my system touched by changes. And that's why we have an integration with Git. It could be GitLab, GitHub, or Bitbucket that you may be using, some cloud-based Git deployment. We integrate seamlessly with Git and are able to analyze commits and also send the updated architecture of a branch into a merge request or a pull request. I will show you that shortly. But what else is this picture telling us? Well, what we see here, for example, in part 5 network management, this is a component which is heavily used, but it's also using lots of things above and below it. So this is what we call a change propagator. Typically, if you see this kind of thing in your architecture, this is the kind of code a developer would be afraid to touch because of fear of rippling effects of making a change. I break something that might work if I change something here. And we all know that anxiety that developers have about touching certain parts of the system. Often when you visualize those parts, it looks like this. It looks like a coupling that has gone wrong. You can also see these components that were sitting on top of the communication, virtual client to file server. They should be independent from each other. We can now create some rules that express that architectural design intent. So we're going to create some independent subsystem rules here. And what that's telling the build system and Lattice is that these components shall be independent from each other. It's an expression of our architectural design intent. And you can see already there's some violations. I have said that these two components should be independent. However, they are coupled through these 20 dependencies. And so you have a red rule violation here. So there are 3 types of rules. The independent subsystem rules. There is also a layering rule that you can apply. If you wanted to preserve this layer, then you could actually create layering rules. And that would then enforce recursively that util, for example, cannot use the com component. And if I, as a developer, come and create a new dependency from util to com, I can be informed in different ways. I could be informed in the merge request. I could be informed in my developer IDE desktop that I've created a bad dependency because we don't want to get any worse. We don't want to see any more erosion. And the third type of rule is the API level enforcement. So you can actually go down to any file in the system. You can expand the members, and that will give you a listing of the APIs available in that particular function. And when you do that, you can then enforce a public API. You could say, for example, that this particular module cannot be used outside. So you're kind of making it private here, and you're preserving that API level integrity. That's also useful for security. You can ensure that any particular piece of data actually is not used outside of a component where it should be. Probably the most famous example is global data. So you could actually create a view of global data here that just looked at the interactions of globals, taking the address of globals, modifying globals, and then you see a much reduced view now. When I apply that filter, you can see exactly which parts of our systems are using global data, which are reading and therefore coupled in that way. And if you're doing control flow, data flow analysis, that's an important use case because control flow can be affected by global data across the system. And we produce a coupling report that is suitable for DO 178C and other functional safety standards. I can do lots of things with this architecture. I could create more structure. If I wanted to say, actually, I want a separate unit now called optional, I could create a new parent subsystem called optional. I could do the same for these two modules and create the required architecture, and then it will recalculate for me the new dependencies based on my modified architecture. So this would be required. And now you can see the coupling between optional and required. We could actually offer up some hints to remove those dependencies now and couplings to make sure that optional really was independent of required. And if you see those hints, we've actually produced a work list that will get you a long way to decoupling those systems from each other. So smart test, and I can do that for any file. I can move things around, I can cut things, I can paste things, and see how that looks in the system. So looking at this architecture, talking about smart build, I can see now these components have no dependencies to each other. They are completely independent. So I could build those separately. And we have a way of integrating with GitOps that says to the build system, these are decoupled and could be built on a parallel hierarchy, for example, using a Credi build or something like that. When people have taken this approach to improve their build times, we saw a medical company reduce their build from 2.5 hours to 20 minutes by taking this parallelization approach. It's also the same for testing. If I can build independently, I can test independently. So we have some good integrations with Cantata from QA Systems that would automatically be able to create integration and unit tests, for example. So here we see part 7 is using diagnostic services 6 times. This is basically the start of an integration test that we can actually use in Cantata. And when we partition, we see the natural groupings of files which actually belong together in integration tests. So you see these components, functions have been grouped together. These files and functions have been grouped together as well. You can then use the scripting with Cantata, which is here, to then create the test projects for you automatically with the correct file setup. So some nice scripting to be able to do that we worked with QA Systems on. And you can also then, the integration tests obviously concentrating on the call sequence level, the expected call sequences. You can then add your functional safety coverage according to your functional safety standard that you're using. So there's a direct integration with the testing tool. And yeah, just a note on the functional safety standards, such as ISO 26262, they talk a lot about architecture. So how do you demonstrate hierarchical structure of software components for an ASIL D system? Well, that's the DSM. The DSM is exactly showing a hierarchical structure. And we've worked with the TUV in Germany extensively to validate our artifacts, and they agree that this is an expression, this is satisfying this clause. Plus the metrics, cohesion, coupling, stability, connectedness are all called out in this standard and the FDA standards and others. We produce a full metrics report as well that you can actually use as part of your functional safety certification evidence. Cyclicality is an interesting one. How much of your system is coupled together with each other? And you can see this part of the system is highly coupled. So very quickly, I'm going to simulate a change now and to a file, to a function in utilfuncs.cpp. I'm going to introduce a new function to this class. I'm going to break some existing Cantata unit tests that I have by making a change in a branch, and you're going to see what happens in the Git workflow in the merge request. So here I go back to my project. I have the code base here, and everything is implemented in a DevOps pipeline as code. So we have infrastructure as code that uses Docker containers. to automate the build, to automate the rules checking, to automate the analysis. And if you're struggling with DevOps and want some help with implementing a pipeline, then we can put together a pipeline that basically automates the building, the testing, the architecture analysis, and the documentation production at the end. And this is the bit that we've spent a lot of time on, the DocOps, because these clauses are hard to satisfy. Not only is there architecture requirements, there's coverage requirements at the unit level that we need. There's traceability as well that's called out in the standard. And maybe you're using something like ASPICE. The ASPICE process is very heavy on this concept of traceability between the different levels. So we have a unique way of showing dependencies between code, test, and the architecture, also in a DSM with our sister product called Tracy. So we want to automate, and so I'm going to very quickly simulate a change and trigger this pipeline now. So let's go to that particular piece of code that we were looking at just now, the utils, and I'm going to make a breaking change to the function that we're looking at here. And towards the bottom of the file, we have a simple function called getCStringCount. I'm just going to break the logic here, change a not equal to an equal to, and then I'm going to do what many developers do but shouldn't do. I'm going to create my bad dependency from utils to the com layer. I'm going to introduce some open source code, which I know has some security issues. And I'm also going to add this function, which has no tests, so no coverage. So I expect my coverage to drop, and it also has some MISRA and AutoZAR violations. And I'm going to create a commit and start a merge request. You'll have something similar in your system, perhaps in the Git workflow. And as soon as I do that, the pipeline is triggered. The software automation is immediate. The DevOps infrastructure kicks in. This particular build is running on virtualized machines with hypervisors, with the GitLab runners, and orchestrated and managed by Kubernetes cluster, which builds that infrastructure. And I don't need to know a thing about Lattice or Cantata or any other tool. I can just execute this pipeline as a user and consume the data that comes back. So essentially what I'm asking now is my software in this branch, in the changes, is it good enough to merge? And in the interest of time, I'll jump to a merge request that I've already done. So you can see what happens when that pipeline finishes. First of all the Lattice data on the architecture is pushed to the pull request. So this is exactly where now I decide, can I merge this code in? And for the first time, we have a holistic view of the software quality, output from different tools, exactly in the place that I need to be able to decide to merge or not to merge. More importantly than the DSM is perhaps the Delta DSM, which shows the differences between this branch and the master branch. You can see that I've made the architecture worse with that change from util funcs to the com layer. And I also have a heat map now that aggregates data from my static analysis tool and my coverage tool. So here I've got some Cantata data that shows the coverage. You can see the coverage has dropped on the util funcs because I added some functions but no tests. And you can see where I'm kind of red, green, and yellow in accordance with MISRA, CERT, system stability metrics. Clearly, I'm not in a good place from a certification perspective here. And this particular branch has a high impact because I'm changing a file which is heavily used in the architecture. So I get that data. I also get the notification that the code quality is degraded. I can jump to the static analysis findings, the MISRA rules, the violation rules directly in my Git IDE. I can also jump straight to the test results, and you see that my test cases for the function that I changed have also failed. So this is pretty much a disaster. My coverage has also dropped here. You see my coverage is now fractional. So I would typically use my issue management system to write my message to Frank saying, we cannot merge. He would then see this in his GitLab workflow. And also we can push those security findings to the issue backlog as well. So we have some open source findings on OpenSSL. We've analyzed those and suggested some fixes to improve. Again, everything being in one place from a security and DevSecOps pipeline perspective. So the main output, however, from the merge request is something that I am particularly delighted about, because I used to spend a lot of time writing these by hand. So if I go to the merge request, you'll see that we output a file that we've agreed with the TUV on its format. Here you can see a detailed compliance report that maps all of those clauses to the tooling that has been run in this particular branch. So you can see which clauses have been covered. You can see which suppressions have been activated, which rules have been satisfied. You can see the architecture, the heat map, the coverage reports, control flow, data flow analysis, everything you need actually for a typical Part 6 compliance report. And we also have a flavor of this for FDA. We have worked with the FDA and a couple of medical companies to produce the same style of report, but for the FDA guidelines. Then the benefit of pipelines is that you can always continue to automate. You can always automate more. So then we came into contact with the topic of traceability. And how can we bring traceability into the pipeline? We spend a lot of time getting the traceability that things like ASPICE needs between different levels. And typically, teams have a dev, they have a test, they have requirements, but there's no one person who can answer the question that from all three domains cross-functionally, or horizontal if you like, to get data to answer these kind of complex traceability questions. So as a classic example, here is an automotive workflow. We start from an automotive hazard, we have a safety goal, a functional safety requirement, and you can see everything should link to each other, to the architecture, to a GitLab issue, to the defect management, a technical safety concept, and back again. And you can have an ASIL rated system and requirements, and you need to show traceability up to that technical safety concept and down to the verification routine, which you can see for an individual requirement. You can go upstream or downstream. However, it's very difficult to see the overview. And so what Frank is going to show now is the traceability, how we can visualize not just source code in a DSM, but also the relationships between different functional safety domains, such as HARA, the FMEA, automotive stakeholder requirements, and find missing gaps in the traceability. So that's also just been added to a pipeline. If you need help with automating those steps, then you can see we now have a traceability step that automates the traceability data between test, your architecture, and the documentation. So I'll hand over to you now, Frank.
All right, thank you, Neil. Michael, can I be thank you.
Thank you, Neil. That was a smashing presentation. Fortunately, we're recording this, so the attendees can replay it in slow motion, I think.
Yeah, sorry about going fast, but we want to try to get as much information in as we can today, and hopefully it will stimulate some questions. Tracy is a new product that we've just recently added, and we're building out the actual mapping of the traceability matrix to the different standards. So far, we focused on ISO 26262 and ASPICE, but we will be supporting the other functional safety standards. And what's really interesting with LATEX, we've always had the ability to create a project in a DSM for multiple systems. So you could have a model, you could have a UML or SysML model, you could have the code, the actual code in different languages. So you could have Java talking to C++ and .NET. And so we have in LATEX created the ability to combine different domains of information, and Tracy is really taking full advantage of that. So the information that Neil just mentioned about taking that the safety concept and the HARA analysis and extracting what's been mapped in a tool such as, in this case, JAMA, but it's also possible to do it with Doors and Polarian and Integrity and other requirements management tools. So getting the information into a multi-domain DSM enables you to literally follow the flow of relationships, and where a relationship should exist but doesn't. In other words, there's some orphans that where there are no relationships, those will be flagged as violations, and it's quite easy to see them in a DSM. Oops. So this is a detailed DSM in Tracy, which shows the actual data from JAMA. So we've got all of the dependencies mapped into each of the domains. And what's interesting is the gaps you can readily see. So for example, expanding the software requirements domain, here is all the requirements. And you can see that there's quite a few of these requirements here that are mapping to the safety analysis, but we have several gaps where there are no relationships. And similarly, the mapping to the software verification of those requirements is also gapped. And these are visible by the empty cells in the matrix. The other unique thing about LATEX is the ability to take our actual architecture. So in a requirements management tool such as JAMA, you articulate by entering the different parts of your architecture. And so these are all detailed here, but that's not the actual architecture. The actual architecture is expressed in the implementation. And with LATEX and the ability to analyze the C and C++ code, we can actually see all of the interdependencies between the various parts of the architecture. And what that means is that we can use the architecture itself to infer dependencies between requirements that have been mapped to the architecture. And so these dependencies you see in the software requirements, those were created by inferring dependencies in Tracy. And that's makes it possible to do an impact analysis. So if in my merge request, I've changed or added things to the architecture that are not reflected in the actual requirements, then you'll see the traceability going from the implementation upstream to the requirements and all the way, in fact, to the safety concept, but also looking at gaps you have in your verification. And so this capability is what we're bringing to the challenge of doing traceability in real time. And as Neil showed, we added the stage, the Tracy stage, to the pipeline. So Tracy is virtualized just as LATEX is virtualized. And we use all this data to then include in the DocOps stage. We're able to include the traceability data into the artifact that is produced. So we have reports then in the verification of the software unit design and implementation that you now can generate automatically. And so this is available if you're interested. We can provide a demonstration, a deep dive for you. We'll be doing a webinar on June 2nd at 1700 Central European Time, which will feature a live demonstration of Tracy, which we don't have time to show today. And with that, Michael, I'll turn it back to you. And maybe we have some questions from the attendees.
Thank you, Frank. Very good. I have a couple of questions here. Will this work with my Jenkins? Is there a plugin for that?
Yes, there is.
Yes.
Ah,
Oh, go
yeah,
ahead.
yeah. There's two ways you can use Jenkins. One is a plugin. There is a LaTeX Tracy plugin for Jenkins, but more commonly these days there's Jenkins in pipeline mode. And just as I showed a YAML file which works with GitLab, we also have maybe I can share again. We have a Jenkins file as well that also does the same work in Jenkins.
And another question.
Yeah, Neil, if you want to.
But yeah, I need the rights to share, and then I can share that file.
Okay.
I can share that. Could you make me presenter, Mike?
Yeah, I make you presenter.
Thanks. Yep. So at the same level as our container here, we have a Jenkins file. So many customers are using. We've actually put a Jenkins library together that does some nice things, like sends the DSM to SonarQube if you're using SonarQube. It sits on top of the Kubernetes pod quite happily. It implements this parallel build step that I was talking about. That's that smart build approach, looking at the independence between systems, and it's a fully automated then Jenkins pipeline as well. In this case, using a cantata wrapper that we wrote to run the cantata tests in too. Yep.
Great. Another question is, it works for C++, but does it work also for Java?
It does, yeah. So with LaTeX, we have different languages that we support. So Enterprise Java is its own profile. If you select Java, you can import directly the jar files of your system, the class files and zip files. We actually have a nice Java demo based on Ant, the evolution of the Ant build system, that we can show you and point you to a demonstration of that. But yes, it's very easy to visualize dependencies with Java. Yep. And also other languages supported Python, modeling if you're using Rhapsody or Spark's Enterprise Architect or some other tool, you can import the model. You can also import Python, C# as well for .NET. There's various possibilities, and we're actively working on other languages like Rust and Go as well. So extending in that direction. And for those using AutoZar, we have a parser for AR XML now, the AutoZar files that you can now visualize dependencies between those. So constant development in the LaTeX team.
Then there is a final question here regarding test coverage.
Right.
Can you generate reports for that?
Yeah, yeah, exactly. So that's one thing I didn't show actually, but if you load up the consolidated view of either Cantata or whichever testing tool you're using, you can produce reports and visualizations uniquely of the coverage results through the prism of architecture. So if you, for example, were interested in the decision coverage, this report could be generated where we have green if your coverage is above a certain threshold, red if it's below a certain threshold, and orange if it's in between. And then you can produce these very nice visualizations that sit alongside your testing tool. In this case, we have also Cantata coverage, the Cantata coverage viewer available. We have the reports that you could generate with Cantata or whichever tool you're using for the test cases, but also for the coverage analysis. And that then is also the full coverage report here, which is a compliance artifact. And then you can visualize that coverage into the DSM. So you can see in the architecture where you need to add more coverage to get statement coverage. And in a DocOps setting, you can really include whatever visualizations you like in the report. You can build your own reports with these integrations, and we can help you to do that we have a lot of library code that helps you to build out those DocOps reports for compliance.
But just to mention also that viewing the coverage through the prism of architecture, it tells you where to prioritize. So if you have something that's in a remote part of the architecture with low coverage, that's not the priority. But if you have something that's being used by everything, like Neil's example on the utilities, then that's something you definitely have to raise your coverage. So it helps prioritize your testing.
Very good. I think that was the questions I had received here. So if there are no more questions, I'll leave it open to the audience for a final chance to ask things. If there are no more questions, we will conclude the recording, and